In this video, we're going to continue with section 2.5 on the intersections of lines and planes, and we are going to do subsection 2.5.2, the point of intersection of a line and a plane, and in particular we will do that by looking at example 2.5.2. So there's a method outlined here for how to find the point of intersection of a line and a plane. Rather than go through the method, I'll do what I did in the last video, which is to do the example and to go and show you step by step when I'm applying the method. So let's read the example 2.5.2 first. And it asks us first to use vector methods to show that this given line and this given plane intersect at a point. And then after that, we're going to find their point of intersection. So let's start here by doing the first part. We're going to use vector methods to show that these objects are intersecting, and we need to remember from our unit on the relative positions that the only thing that we need to do to show that the line and the plane intersect at a point is to show that the normal vector of the plane and the direction vector of the line are not perpendicular. In other words, we need to show that the direction vector dotted with the normal vector does not give 0. So that's what we'll start with here. We can see the direction vector of the line as -1, 1, -3, and we can read the normal vector of the plane as 1, 2, -1, and so d dotted with n gives me -1 plus 2 plus 3, so that's 5 minus 1 is equal to 4, which is obviously not 0. And that is all we need to do to show that L and pi intersect at a point. So they intersect at a point. So that part is done, right? That first part is done. So now we can go ahead and learn the method to find the point of intersection. So in this method box here, it says to find the point of intersection of a line and a plane, we can use the following procedure. And it says, first of all, that we should write the line in parametric equation form and write the plane in general equation form. Well, the plane is already given in general equation form, so that is done. So let's go and write the line first in its parametric equations. So if we do that, remember we're reading component by component, x is 2 minus t, y is -3 plus t, and z is -3 minus 3t. So that's the first part done. The second part says to plug the parametric equations of the line into the equation for the plane and to solve for t. Right? So that's the second step here. So let's go ahead and do that. So the plane equation is x plus 2y minus z is equal to -9. If I take the equations of the line and plug those in, well, I'm getting x is 2 minus t, plus 2 times y is -3 plus t, minus z, so -3 minus 3t is equal to -9, and solve for t. So 2 minus t minus 6 plus 2t plus 3 plus 3t is equal to -9. If we collect our t's here, so we have 5 minus 1 is, so 4t is equal to, and then collect here the constants, so 2 plus 3 is 5, minus 1, bring the 1 over to the other side, so 4t is -8, t is -2. So we finished the second part. We've solved for the parameter t, but that's not what the problem is after. We want the point of intersection, so we're going to do step 3, and that is to plug t back into the equations of the line, right? So we'll take the equations of the line here. Let's copy those down. Here they are. I guess we can get rid of the number 1. And we're going to plug t back in. So t is minus 2, so 2 minus, right, this is at t is minus 2. Plug minus 2 in, so 2 minus minus, 2 plus 2 is 4. Minus 3 minus 2 is minus 5, and minus 3 plus 6 is 3. So our point for minus 5, 3 is the point of intersection of of our line and the plane. And that's it. That's all you need to do to find the point of intersection of a line and a plane.